Hello everyone. Today we're going to continue with our second video on the Fourier Transform. On the first video, we introduced the concept of the Fourier Transform from a conceptual perspective. Now we're going to start working the mathematical algorithm of how to solve the Fourier Transform, how do we convert mathematically a time function into a frequency function. Okay, so the Fourier Transform itself, by applying the Fourier operator into a function of time, we get a function of omega. You want to notice the difference in the structure. A time signal usually has a lowercase letter, while a frequency signal has a uppercase letter. So the Fourier transform is the integral from negative infinity to positive infinity of the function, the time signal, multiplied times e to the negative j omega t dt, right? If we want to bring back a function of omega back into the time domain, we can apply the inverse Fourier transform, which is by applying the inverse Fourier transform operator, cursive f to the negative 1 of the frequency signal as a function of omega. That will give us a time signal, which is equal to 1 over 2 pi, the integral from negative infinity to infinity of the frequency function times e to the j omega t d omega. There's two differences in here between the Fourier transform and the inverse Fourier transform. If you notice, everything in the Fourier transform is a differential of time, so we're integrating with respect to time. And then our mapping element, which is the exponential, is a negative j omega t. In the inverse Fourier transform, we have differential. We integrate everything with respect to omega. The mapping element e, it's j omega t, so it's not positive. So it's not negative. It's positive. We're integrating the function of omega, but here's the interesting element, and it is that we have this term, which is kind of a coefficient that it yields from the conversion, and it's 1 over 2 pi. Okay, so this term we'll keep seeing it as long as we keep working from one domain to the other one. This form of 1 over 2 pi will keep appearing, and we will use it when we're transitioning from one domain to the other. Okay, so we will do several examples, and you'll see how this 1 over 2 pi sometimes become 2 pi if it's convenient to send it back to the time domain. Okay, so let's do several examples. First of all, let's work with let's calculate the Fourier transform of several functions, several known functions that we have worked with in the past. And I want to start with the Dirac function, the delta, the impulse function delta t. Okay, it is vital for us, before jumping into the mathematical algorithm, to remember the sifting property, right? So what is the sifting property? The sifting property states that if we want to integrate from negative infinity to positive infinity, the delta function times any function of time dt, the result will be the primitive of the function, but evaluated at 0. Okay, so the function itself evaluated at 0. Why? Because the impulse response fires up at a t equals to 0, meaning that if we want to change the place or the time where the delta operator is firing, then the result of the sifting property states that we will have the primitive of the function, but being fired at t naught. Okay, so that is the main concept in here for this term. So in other words, if we want to calculate the Fourier transform of the delta function, then we pose the definition of the Fourier transform, right? So in this case, we'll have integral from negative infinity to positive infinity of the delta function times e to the negative j omega t dt. The result of this will be just e to the 0, okay? So e to the 0, we know that this is equal to 1, right? So the Fourier, we can conclude that the Fourier transform of the delta function is actually equal to 1. All right, very similarly, if we're looking to calculate the Fourier transform of the impulse function but fired at t naught, right? So very similarly, we apply the shifting property, right? So the frequency function, the result of this will be the integral from negative infinity to positive infinity of the delta function fired at t naught e to the negative j omega t, and this gives us a result e to the negative j omega naught. Sorry, I made a mistake here. It will be negative j omega t naught. Okay, so this is by applying the shifting property. All right, let's move on. So if we want to calculate now, if we want to find what is the Fourier transform of e to the j omega naught t, okay, so let's just use the definition of the integral of the Fourier transform. So in this case, we have that x of omega is the integral from negative infinity to positive infinity of e to the j omega naught t times the mapping element negative j omega t dt, right? And this is equal to, if we combine the terms, this integral in here, and then we just have one exponential, and we can actually summarize this by writing it as jt times omega naught minus omega, okay, dt. Now, there is an interesting property in here, so we will use this. This is called the duality property, but let me just pose it based on the previous example. So we know that the Fourier transform of the delta function is actually equal to 1. But what if we want to find the inverse Fourier transform of 1? Then by the definition we will have 1 over 2 pi integral from negative infinity to positive infinity of 1 e to the j omega t differential of omega. And we know that this is actually equal to delta t, okay? So here is what I was mentioning. I'm gonna send this 2 pi to the other side, and we end up having that 2 pi, the delta function, is actually equal to the integral of negative infinity to positive infinity of e to the j omega t dw. Okay, so why is this relevant? Well, because what we can do here is we can try to see this integral that we have here, okay, the original one, and see if we can somehow, this is an improper integral, so let's see if we can convert it into something that we can use and manipulate, okay? So this is what we're gonna do. So I'm gonna say that the delta function, in this case, if I say delta of a is actually equal to 1 over 2 pi integral from negative infinity to positive infinity of e to the j a t dt, right? So if we multiply by both sides, we end up having exactly the same thing. Like if we end up multiplying everything by 2 pi. So 2 pi delta A equals integral of infinity to negative infinity of e jat dt. Okay. So you see this relationship in here, right? So what that means is if we say, what if A is equal to omega naught minus omega, then we actually get what we want, which is f of omega will be the integral from negative infinity to positive infinity of e to the jt omega naught minus omega. And what this is equal to is 2 pi delta omega naught minus omega. Now, because this function is actually even, right, it fires up symmetrically, we can actually also claim that this is actually equal to 2 pi delta omega minus omega naught. Okay, so this is the Fourier transform of e to the j t omega naught. And this is a very powerful statement because it actually tells us that the Fourier in the Fourier spectrum of e to the j t omega naught is actually a spike, which is a delta function that is being fired at omega naught, right? So that's the implication of this, that in the frequency domain, this exponential function in the frequency domain will be firing up as an impulse response at omega naught. Okay, so how is that similar or different if we're actually working with a cosine, right? So if we remember from our friend Euler, right, the exponential format of cosine, right, cosine of omega naught in its exponential form is actually 1/2 e to the j omega naught t plus 1/2 e to the negative j omega naught t, right? And these are integrals that we can apply on the Fourier transform, right? So we can actually perform the integral or the definition of the Fourier transform, the integral from negative infinity to positive infinity of 1/2 e to the j omega naught t times e to the negative j omega t dt, right, plus 1/2 integral of negative infinity to positive infinity of e to the negative j omega naught t minus j omega naught t. Okay, so if you notice, this is just the definition of this result that we got here, right? This is exactly what we have in here. So meaning the Fourier transform of cosine is just 1/2 2 pi times the firing of the delta function at omega naught and at negative omega naught. So contrasting to what the exponential was offering, the Fourier transform of cosine is actually two impulse responses, one firing at omega naught and the other one at negative omega naught. Probably you noticed this effect on the introductory video where I was working with the signs of C, E, and G, and I was writing spikes both on the positive plane and on the negative plane, right? So that's how this definition comes into place. And what does it mean to have a negative frequency? Just think about it for a minute. But as we have discussed in class, it just not necessarily represents frequency, but angular velocity, right? Which could be positive or it could be negative. But because of the complex nature of the imaginary nature of the cosine, we actually need to have the mathematical response both on the positive side of the plane and the negative side of the plane. Now for homework, I will ask you to find what is by definition the Fourier transform of sine. And let me just write from our friend Euler, what is the definition of sine, right? So sine is just 1 over j2 times e to the j omega naught t minus e to the negative j omega t, right? So from this, I'll ask you for homework to, by using the definition of the Fourier transform, to calculate what is the Fourier transform of sine, okay? Okay, we'll pause this video here and I'll continue with more examples later. All right, bye-bye.